Now we're going to continue in the compressible flows and its significance and its effect based on what we already checked before. So what we checked before for pumps and turbines, it was water or incompressible flow. Now we have a centrifuge compressor or an axial compressor or centrifuge fans or blower or a wind turbine or fans and the gas turbine or the steam turbine axial type. So what is the signification of having a compressible flow? First, let's take the centrifuge compressor. Centrifuge compressor, which is having a runner or an impeller and having a guidance diffusers, yet it is a diffuser. We're going to discuss about it right now, why we say it is a diffuser, and the outlet will be from after the case itself. Okay, what has happened? What has happened is air enter from the middle, will go here, impeller, rotate, give a kinetic energy, and change from the kinetic energy to potential energy in the diffuser, then out again to outside. So the work done to the compressor, it is at the runner itself, and whatever is happening as a diffuser area is a constant, assuming as a constant, not change in the enthalpy, which means there is no any power or work has been generated or given to the air here. We are assuming that is whatever work is getting been injected inside the compressor itself at the runner, it is an isentropic case process. Then we're going to check, this is the ideal case, and we're going to check if it is not an isentropic, which is the actual case, how we are going to manipulate with it. So based on the rotation and the V is vertical here, similar like what we discussed before. So you have U and you have V is vertical, then the air will go like this. So based on no shock, and similar like centrifuge pump, water go like this, so V will be in the direction of the plate, and there is no whirling velocity, which we need to understand. It is still similar like centrifuge pump. There is no whirling velocity at the inlet, which is equal 0. It is all radial, and here is a point, which is the runner, not like the centrifuge pump. Here in the centrifuge compressor, the runner or the impeller is giving the relative velocity from the plate or the angle. It is almost radial, which is mean, if you remember, it is this case. So a centrifuge compressor, we are manufacturing it, or it is manufactured to be ensure it is a radial outlet only, which is mean beta 2, or the angle of the plate at the outlet of the impeller should be equal 90. Why? Because here we didn't have a diffuser, we have a violet case. Here we're having a diffuser, and this diffuser, it is acting as changing from the kinetic to the pressure energy. Okay, so while this one is V relative velocity here, so this one is U as the rotation is like this, so this one will be V2. Okay, the actual V, and of course VR1 from this shape is equal to V, so VR2 is equal to VF, or velocity flow. Okay, and it is the same as here, by the way. Okay, okay, so from this, that we know that like this, the x component, or the component of V2 in the rotation direction, it is exactly equal to U. So VW2 equal U2, which is, we can state it directly even without writing from what we discussed before. Yes, as we know that is the energy for the pump, it is VW2 U2. If VW2 and U2 is equal, so it is U2 squared. Okay, which is U2 squared or VW2 squared, and the H is over G. It is the same concept, same philosophy. Yet, still, we know there is same concept. There is a slip going to happen. Here high pressure, here low pressure, here high pressure, here low pressure. So slip going to happen like this. So we know that this is a theoretical energy or a theoretical head. In case of a slip, multiply by the slip factor, and the energy to the shaft, it is same concept. If I'm giving an energy to the shaft, so we know that is the energy of the shaft here multiplied by psi multiplied by the theoretical head or energy as psi bigger than 1. Okay, which is, we name it is a power factor input or a power input factor. You can imagine if it is an efficiency, so it is this one divided by this one, which is will be less than 1 if it is a compressor mechanical efficiency, or if it is written as a power input factor, so it will be bigger than 1, so which is this one over this one. Okay. Till now it is copy paste of the same philosophy of the rotated blade in the centrifugal compressor and the pump. So the question is, where is the compressibility significant, and what is the diffuser going to do? So before starting with all of these items, we need to define, while any airflow through a diffuser, we know that in case of the no heat transfer, it is similar like converging, diverging duct, or a diverging duct, or whatever. So we know that is B stagnation is equal to B static, or the static head, plus the kinetic, or rho V square over 2. Case of no friction. Of course, there is a friction, there is an internal energy, if we remember. And the same case of enthalpy stagnation, enthalpy, as we discussed it before. So, based on the above, we can state that CB, which is, we name it, this one is the most general case, if you remember, and in case of no friction, but we know now that we have a friction. So if we are going to use this one, and this is which you're going to use, and we know that is 1, which is here, equal to velocity enthalpy here, which is plus the velocity here, equal the stagnation temperature. So stagnation temperature, we can rewrite it like this. And we know stagnation temperature 2 is equal to stagnation temperature 3, which is in another word that if we know the total power input here, it is m dot multiplied by CB multiplied by S3 minus S1. The total power has been entered, and we put it as a stagnation. It is okay, because if you put it as T1 minus T2 and V1 minus V2, it is the same. Okay, so CB stagnation 3 minus stagnation 1, which is will equal stagnation 2 minus stagnation 1. So from this one is equal based on thermodynamic, and this one based on velocities diagram and fluid mechanics. So this term is equal to this term. Okay. Till now, what we agreed that is it is a stagnation, which is mean, or what we are doing, it is based on isentropic case. So if it is not isentropic, okay. If it is not an isentropic case, imagine that is we have B stagnation 1 and B stagnation 3, and this is temperature S diagram. So you will have in constant S from stagnation pressure 1 to stagnation pressure 2 at temperature stagnation 3, but we keep it dash. This is isentropic. Actual case, it is in the increase of the isentropic, so it will go in this direction. So we know that we going to know that eta isentropic, or the efficiency isentropic, which is the total energy based on isentropic process divided by the total energy actual. Of course, the isentropic is the most less energy. So if I told you that the isentropic efficiency of that compressor is 90%, so you know these numbers, and you know this number. So stagnation, it is 1s. Stagnation temperature 1s, and stagnation temperature 1s, and stagnation temperature 3s. It is as isentropic from the isentropic process. It is, you can get it from thermodynamic tables, for example, for an isentropic process, or you can apply as an isentropic relationship like BS3 over BS1 equal TS3 stagnation dash over TS1 stagnation, which is, it's very easy. Okay, gamma over gamma minus 1. It is the relation of the isentropic process in thermodynamics. So while you know this, you can get this one. Of course, this one you can get it very easily. This is an input to the compressor. And this one you can get it from pressure ratio. So based on the pressure ratio, you can get this one. Based on the efficiency of the isentropic, you can get the actual TS3. Based on the actual TS3, you can go back and write this equation. From where we got this equation, it is very simple. It is this equation. It is this equation. Just multiply this one here, then put it in another here and here. So it is CB TS3 minus CB TS1, which is this one. So it is CB TS3 minus TS1 equal to this term. So you can calculate the total energy. From the total energy, you can calculate the velocities. Or for example, if you know the velocity, so you can calculate. Normally, if you're going to do the CFD, they're going to ask you what is the slip factor for the compressor, or what is the isentropic efficiency of the compressor. So if you want to take what is the isentropic efficiency of the compressor and the slip factor of the compressor, you need to know what is the pressure ratio. If you know the pressure ratio, you can get in a case how much forces or pressure or torque you're going to have from the torque omega, and you will get the energy. From the energy, you can get what is exactly these two terms together. But because in CFD you don't care about friction, because you're not simulating the bearing or like this, so you can get directly the slip factor. This is the first term. When you have the slip factor, while knowing all of this information, and you know these temperatures, and you put the number which you got equal this one, so what you will get, you have the slip factor of everything. You can get actual TS3, or you can measure it from the CFD. If you measure it, you can take the isentropic efficiency. So when you have a model and you simulate it, you can get slip factor, you can get for that model, and this will be your results. Okay, so this is also, it is up to you. You can define the pressure ratio. You can put from here CB by CB, so you can put from this one inside, and you start to make algebra. Then you will reach that is the pressure ratio between 3 and 1. It is 1 plus eta psi sigma U2 squared over CB T1 stagnation, which is mean it is all like constants for certain compressor, which is means the pressure ratio is a function of square root of the rotational velocity. Okay, you can manipulate algebra, or you can use it, up to you, this way, that way. It is not a big deal. Here, of course, there is gamma over gamma minus 1. It is, uh, 1 second. No, no, no. No, it is correct. Because this is pressure ratio, it is a relation of temperatures. So it is gammas. Or it is a relation of the velocities. Okay, so it will be without gamma. Okay. Now, what is our approximation, or so what is our understanding which you need to do? You need to identify if you're doing a simulation or CFD or etc. You need to check that is you don't have a Mach number less than 0.3, because if you're going to have a Mach number here less than 0.3, the fluid will not be compressible, so it will not work as a compressible. It will not work as you will not compress air. So you need to ensure that your Mach number is bigger than 0.3, and you need to ensure that your Mach number by anyhow, anywhere, whatever, less than 1, because you don't have shock. Because when you have shock, all the velocities profile, diffusers, etc., the air stop to know what is happening outside. So you will get a maximum mass flow rate. If you remember, when the air reached shock, it reached to a maximum flow rate, and it is going to, whatever you're going to inject power in the system, nothing going to happen. Okay, so usually Mach number should be between 0.7 to 0.9, anywhere inside that at the impeller here itself. Okay, it's just to identify this when you are doing. Also, you need to understand that the diffuser itself. Let's discuss about diffuser. The diffuser itself, which is, this is the first area, this is second area, this is the second, this 0.1, this 0.2, this 0.3. So if you start to state that as the mass flow rate is a constant, it is a fact, which is equal to rho v area, which is v dot, by the way, the volume flow rate. So because the mass is constant, and we know that is we are over Mach number 0.3, the density going to increase. So when the density is going to increase, so this is a velocity, it's not a volumetric flow rate. This is a volumetric flow rate. So when we know that the density going up with constant, so velocity must go down, and area too must go up. Just a derivation how it is will be. Okay. Okay. Again, if mass flow rate is constant, density is increasing, so this term must go down. Agreed. This term to go down, either the velocity needed to be go down, and if the velocity needed to be go down, so you need to manipulate with the area. So you need to increase the area. Okay. By the way, this is the wrong direction. It should be like this. Okay. Also, we need to understand there is something named slip, and this is same what if the pressure is upstream is higher, so maybe it will be a reverse flow as of the slip on the bar. So it's not slip, the separation at the plate itself, which is may occur, and we need to ensure it's not happening. A separation. Okay. So you need to identify, do you have a separation or no? Okay. Now in the axial compressor. Axial compressor, it is not like centrifuge compressor. Axial compressor, it is a multi or a rotating rotor and there is a stator. The stator having an inlet guide, then a diffuser, then a diffuser, then a diffuser, and this one is a blade impeller or a rotor impeller and rotor impeller or a rotor, which is the flow is going like this, then inlet guide, then rotor, then diffuser, then rotor, then diffuser, then rotor, according how many stages. What is the pressure is going to be happen? If you have the pressure a little bit, there is loss in the pressure due to the friction, then increasing the pressure, then in the diffuser also increasing the pressure as we agreed, while the velocity is here is almost constant, then the velocity increased kinetic energy in the rotor, then the velocity decreased due to the diffuser changing from kinetic energy to the potential energy, and the compressor axial compressor design to ensure that is it will return back to the same state. This because we don't want stresses on the rotor, so the velocities need to be returned as a direction and the magnitude again after the diffuser. So the diffuser is reacting the same condition here back again. So again, jump up, come down, jump up, come down, but the pressure start to go up, go up, go up, go up, till which pressure stage you want to reach. Okay. Now we need to understand. We are going to to study it at the mean diameter, which is mean not the tip, not the bottom, at the mean diameter. And we need to know that as a mass flow rate, as we discussed before here, a mass flow rate, here is not is a volume flow rate, it is V flow multiplied by the area, and the area is by dB. Here the mass flow rate, same concept but multiplied by rho. Here the mass flow rate, it is rho area multiplied flow velocity, but yet we need to know what is the area. Now, before the area, we agreed it is by the B, and B is the width of the plate. Here, the area is by D mean diameter, multiplied by the height of the plate. Okay, it is the same concept, but here is name height. It's not mean. Okay, now let's check the angles. Like here is the rotor and the air entering like this and getting out like this, to check the angles to get the work done and etc. And to even study something which is related to what is the mean of work done factor and etc. and why we don't have work done factor here. What is this term? We know the slip, but we don't know work done factor. Now let's zoom. First of all, if this is a plate, so we know there is a relative velocity with the same angle of the plate will enter. We know, and because rotation is in this direction, so the component of VR in the rotation direction is this one, and we know U is this one, so V is this one. Okay, in another way, let's do it in bend. If you have, this is VR, so in and okay, so this one we are in the rotation direction, and the rotation direction is upward. So I know that is the rotation direction upward, so I will draw it in blue. And this is U. We know from before that is component of the actual velocity in the rotation direction is equal to this one vector by vector plus this one in vector. So this one plus this one in vector, so it is this one. Okay, which is will mean actual velocity is like this. Of course, this one is bigger than this one, so the resultant will be like this. So from the same start point, and this is V1. Okay, same. Very simple if you just understand the definition. Okay, so this will be V1. So this one will be V flow, and we agree that this V flow is equal everywhere. And we know that because we need everything to return back to each original condition again, so we know that is beta here should be equal to beta here, or the plate angles. It is not written here, but however, no, it is written here. Beta, or because alpha is 90 plus beta, or you see, this is alpha, this is beta. Okay, so we know that is alpha here equal alpha here, or beta here should equal beta here at 3, yeah? Not 2. 2 is different. But 1 and 3 should be remaining as a magnitude and the same. So V1 and V3 equal. Alpha 1 and alpha 3 equal. Beta 1 and beta 3 is equal. And we need to know by anyhow that is V2 should be bigger than V1. By anyhow, we should still I didn't discuss about this one. By anyhow, also we need to know that is Vf1 should equal Vf2. We need to know because we are dealing at the main diameter, so U1 should equal U2 and V1 equals V3. So this is from just the diagram. We understand all of this, except this one. We're going to check it now. Okay, if you are going to check what is the whirling velocity is the component of actual velocity in the rotational velocity, which is this one. So this is the tangential velocity of the whirling velocity, which is we're going to gain it. So this one multiplied by this one minus this one multiplied by this one, you will get the energy. Okay, how to calculate this one? It is very easy. This is relative velocity in this direction, u in this direction, the component of relative velocity down, and this one up. This one will be plus this one, but this one in opposite direction is minus, so this one will be upward v component of in the rotation direction. So this is the start point, so it will be v2 like this. So the x component, so the component of v2 in x direction is the whirling velocity. So we can, as we discussed, we can write that is the energy or the power, dot energy is the power which has been injected in the axial compressor is this one. We know it's u1 is equal to 2, so put u outside. So it is whirling velocity 2 minus whirling velocity 1. Now we need to define something named a work done factor, and also we need to recall what we already studied in the previous compressor regarding the stagnation. So we know that the stagnation temperature 3 minus 1 equals Cb. We know this one, and we know that of course this is a one stage. This for one stage, which is mean in out, yani rotor and diffuser like this. Okay, and we know that there is no any work done going to happen inside the guidance inlet. So we can write it as 2 from 2 to 1, or here in diffuser from 2 to 1. So it is Cb Ts2 minus Ts1. But we know that this term, we know is this term is equal to this term plus the velocity term. Okay, the velocity term, which is 2 and 1, which is the difference between 2 and 1. Okay, same what we have, what we done here before about the velocities. Okay, if you put here, by the way, here is missing. We didn't write it, but if we try to write it, it will be v2 over 2cb minus v1 over 2cb squared, like here. Okay, and you will multiply to cb, so cb will come. Okay, so we need to write it here. I will write it now. Okay, it will be similar like this one. Okay, so now if we want to define T3S, as we agreed, this is based on the isentropic process. If it is not isentropic, same process, same concept, this is isentropic efficiency. From these numbers and this from this one, I can get TS actual. When I have TS actual, I can put it here, plug the number, blah blah blah, etc. Then I can have the pressure. Okay, till then. Okay, same procedure. Okay, now let's define what is work done factor. We know before here we have a slip factor, which is because it is rotating, so it's slip. Now in the axial compressor, we don't have that slip factor. Why? Because it's axial flow, which is mean if here, so it is rotated in this direction. So if here is higher pressure than here, yes, but it is like this in rotation, this, but because it is rotated like this pressure here is higher than this one, and if the slip is going to happen, it needed to happen like this. But because there is no change in the pressure between this one and this one, so there is not going to be happen a slip, but something else is going to happen. What is going to happen is the work done factor. Work done factor, because of the air at the first stage, it is like this. And when you go in other stages, the uniform of it start to be, the velocity profile start to be like this, and this is h of the height of the plate. This is due to the axial flow is not uniform over the plate height, and while start to go like this, it is more jetting in the middle, and because here it is static, so it will be at the edges is way a little bit static, or a little bit like this, so it is not uniform. And while we have a multi-stage, more and more ununiform flow happens. Ununiform flow happen, which is means the resultant average, or the resultant velocity, because we assume that the velocity is equal, is constant here, or a certain number, so it start to be reduced more and more, which is shown as the work done factor, based on the ununiformity of the flow. It is from 1 to 0.8 when it is go to multi-stage. Why it's not happened here about the uniform? We don't care about it because we have only one stage, which is if you go here in one stage, it is almost one, so no need to open it. Okay, at the centrifugal compressor. Okay, now we need to define something which is named a degree of reaction. Degree of reaction, it is a definition also. It can be asked, what is the degree of reaction of that model? The degree of reaction, it is the total, what we get, it is like this, what we get from the water divided by what we get from the water plus what we get from the stator. Okay, in another way, the enthalpy gained from the water plus divided by the enthalpy gained from the water plus the stator, which is you can write it in a way of the velocity, which is about the tens of Vf and U, or you can and also you can identify it from whatever else. Okay, so what is the benefit of it? No, it is very, very, very high benefit. It is cutted here, but I will try to add what is cutted. In case of a degree of reaction of a compressor which is equal 0.5, so there is a similarity. This is after long derivation, by the way. You're going to put the velocities, etc. So you will reach to this formula. However, in this from textbooks, so in case of 0.5, it is named as symmetrical plate, which is states that is alpha 1 and beta 2 and alpha 3 is equal, which is also states that is alpha 2 equal beta 1. This is 1 and this is beta 1. And if you have all of this condition, so something named is the flow efficiency. Flow efficiency, it is Vf divided by U. So you can define what is the flow efficiency. Okay, it's just some but when somebody tell you that is our compressor, or the compressor degree of action of the compressor is 0.5, or you find that is alpha 1 equal beta 2 equal beta 3 and alpha 2 equal beta 1, if you find all of this condition, which is mean it is symmetrical plates, or the degree of reaction equal 0.5, which is mean whatever you get from the water is half of whatever you get from the water plus the stator, which is mean whatever you get from the stator, it is equal to what you get from the water. What do you get from the stator? As we discuss here, this form, sorry, from 2 to 3, the enthalpy you get from the stator. Okay, this one just a definition in case if you have a case, and in the case written symmetrical, so you need to understand from symmetrical plate what is mean, or if it is written it is degree of reaction equal 0.5, or this alpha, so you can understand. But mainly you need to do, it is just the definitions to understand it. That's it. Now we are going to check what is wind turbine or fans. Wind turbine is exactly the fans. exactly the fans. Yet when we are dealing with the efficiency, we need to know that is in the fans, the efficiency needed to be bigger than 1, and in the turbine, the efficiency less than 1. That's it. Same equations, same everything. So torque is half O area U squared CD, and power is 1 over 4 rho area U cubed. Then we're just going to discuss the factor. Okay. As we agreed, we need to know how we got this formula. Okay, bear with me. Open the paint. Even this one, we don't need to draw the velocity profile because it is way, way, way easy to note. Imagine that, not imagine, we know you have, sorry, we have a kinetic, assume it is a turbine right now. We have a kinetic energy represented in V, velocity, going to be in an X box, and this kinetic energy will be converted to power. So the first question what you're going to ask yourself, what is my kinetic energy? Your kinetic energy is half rho, or whatever, let's write it in the simplest way, half m v squared, which is assumed that the entire v has become a 0. Okay, the full velocity is become a 0. It is theoretically, it's not correct, but it will be like this. This is the full kinetic energy. So the full kinetic energy, which is, we can write it in a way of rho multiplied by the area here, the area, right? So rho multiplied by the area multiplied by the velocity, which is, the velocity is, can be written, we have two velocities. The first velocity is length per time, right? And this area, it is this length also, by the way. So mass is area length rho. Okay, first velocity length by time, second velocity length per time. Okay, so this one is energy, how many joules has been injected. Okay, if I want to check what is the power going to be injected, so we know joule per second, so it is 1 over T. We're speaking here, huh? And there is here half. Let's arrange what we have. This one is a velocity. This one is a velocity. This one is a velocity. So we can rewrite it as half rho area velocity cube. Okay, this is how we can get, even without putting the velocity diagram. Even if we're going to put the velocity diagram, we will reach to the same concept, same results. Okay, it is very simple. Okay, yet we know that is not the full kinetic energy going to be converted, as the exit velocity will never be 0. So we know this one is theoretically, so there is an efficiency of the turbine which is less than 1. And it's a similar case, efficiency of fan, not efficiency, but this power factor of the fan, power input factor of the fan should be bigger than 1. It's due to that it is impossible that we can reach to 0 velocity out, which has been written here. Okay, what I already described, that is, it is impossible you are going to take the full energy of the kinetic energy in the turbine. It's defined by one guy, his name is Betz limit. Bed's limit, it is that he stated that is the efficiency of a stationary actuator disk for wind turbine. It is like this, which is after a long division, which is B divided pressure A, which is 16 over 27. So it is 59.3. He done a long division. That's based on the concept what I already stated. Impossible you will get if you start to reduce more and more the exit velocity, you are reducing the mass flow rate, you are reducing the mass flow rate, you are reducing the power you got. If you're reducing the power you got, you are reducing the efficiency. And if you're increasing the exit velocity, increasing it, yes, you are increasing the mass flow rate and you're increasing the power, but you are decreasing the power in another hand, or the efficiency of extracting the energy from kinetic energy, which is you return back to decreasing the efficiency. So it is double sword edge. So he said that the maximum efficiency based on this phenomena is 59.3 after long division, and this is percentage which is the upper limit. So for any CFD model, whatever you're going to do, and you find that is your efficiency is, for example, in the turbine, let's say 45 or 48, and you say no, the turbine is not efficient, take care, you will be a specialist. So you need to know that no, this is really high efficiency. Okay. And of course, if you get more than this number, something wrong with your calculation, something wrong with your model or whatever. Okay, so we understand this part. Okay, we need to understand also the other parts. Uh, by the way, the wind turbine actual efficiency, it is between 16 to 46 percentage. This theoretical one. Theoretical one maximum is 59.3, 0.3. Okay, so just to remember the water turbine, what we discussed, the Kaplan and Francis turbine, the efficiency of water turbine is from 80 to 90. Okay, why this one can reach to this high numbers, yet the air turbine cannot reach to this number? It is for small principle of for the pressure of the air. Pressure of the air, power of the air is this one. Power of the water, as we discussed it before, it is this one. Okay, so the available head you can get it from the water is way huge if you compare it, because from the water we are converting the potential energy to energy, useful energy. Potential energy has no any function with the velocity itself, yet we are changing from potential energy to the velocity, from the velocity to whatever, but this is what we got. But in the air, we are changing the kinetic energy what we have, and the kinetic energy what we have, it is very limited. You need to have very high input speed. Okay, this is why even you can say that this water turbine is having higher efficiency than the, okay, and even it's having higher power, by the way. Water can go from 5 kilowatt turbine to 100 megawatt. Air turbine maximum it will be 7 megawatt maximum, from 0.8 to 7 mega. It is usually 1 megawatt. Okay, just to have a small comparison. So, by the way, this efficiency didn't take into account any other losses, huh? The mechanical losses itself. No, it's not taking into account any mechanical losses. Okay. This is what we discussed. If it is slow wind and must zero, and if you're going to stop the wind fully to get, but you will have zero power. Okay, this one we finish. It's copy paste, but please, efficiency is needed to be bigger than one for the mechanical efficiency regarding the fan. Same concept, but here work output, here work input, and that's it. Okay, CD is it is a coefficient, by the way. It is not a big deal. Okay. centrifuge fan or blower. Centrifuge fan or blower is different than the fan. This is an axial fan, or this one an axial. Wind turbine is an axial turbine. So this one is centrifuge fan. Centrifuge fan is different than the compressor. Centrifuge compressor. Centrifuge compressor having a diffusers with an impeller. Centrifuge fan, we name it blower. It is same, but there is no diffuser. There is no diffuser here. Okay. So what is the difference? The difference here Mach number above 0.3, which is it is really compressing the flow. Here Mach number less than 0.3, which is mean it is incompressible flow. We're just giving a head. We're increasing the pressure of the air, for example, like in EHUs or whatever. All of this application, all of our HVAC application, it is a centrifuge fan or a blower, or it is a fans, an axial fans, which is the air can be assumed is not pressurized. I will give you an example. The maximum you deal with pressure for an EHU, how much? 500 Pascal? Okay, 1000 Pascal? What, 1500 Pascal? Okay. Let's say 1000, let's say 1000, let's say 2000 Pascal. Okay, it is 2000 Pascal. What is the pressure of the air? It is 10 to the power 5 Pascal. So let's say 2000 Pascal divided by 1, 2, 3, 4, 5. Multiply by 100. You are compressed the air less. Oh, yeah, the maximum is 2%. So imagine that is you make a compressible flow, or you are assuming it is 2%. It is nothing. So we can assume, even if you can assume it is incompressible flow. By the way, if you are dealing with it, assume it is an ideal gas incompressible flow, and that's it. Okay. So centrifuge fans or blower, it is similar like centrifuge compressor without diffuser. Yet now here we are in a freedom not to be all radial. We kept it all radial here, outlet, because there is a diffuser here, and I want to ensure that is the air coming from the impeller here, or from the runner here, or whatever, is the flow is with the same direction of the diffuser. Otherwise, I'm going to have shock. I'm going to have increasing the Mach number, by the way, like more flow going to inject in one area, but less flow going to inject in another area. So more flow, which is mean more velocity. So I will be shocked, which is mean Mach number equal nearby one, especially when we are dealing, by the way, nearby Mach number 1, and we want to reach 1. So we need to ensure it is all radial, the design itself of the compressor. But now, because here we don't have such case, no diffuser, it is violet case, I don't care. So we can provide a backward plate, radial plate, or forward plate, similar like the pump. Same concept like the pump, same what we done like the pump. This is VR out, and we know this is U direction, so vectorial component. So this is the remaining, so this is viewer link, this is viewer link, and this is viewer link, what we discussed before, beta 2 bigger than 90, equal 90, etc. And whatever. So we know from the above curve that is the whirling velocity in the forward curve is bigger than backward curve, as we discussed before, which is resulting that is giving me more head, more energy, like what discussed before here in the pump. It's the same concept like in the pump, by the way. That yes, because the whirling velocity is so it's giving us, see, it's giving us the curve is higher than this one, than the orange one. Yes, it is giving us more power. It is the same. I'm going to repeat the same statements. Yes, but take care that same concept, that is, it is not self-limiting, and etc. It's a part load and whatever. Okay. even it's not stable or whatever. Okay. Uh, Now we are going to discuss the head and the energy equation, which is very simple, to close also chapter of blowers. And okay, now we're going to discuss about the head. Now, because we know there is an impeller going to rotate, so there's an increasing in the head here, and due to the violet casing, there is an increase in the head in the helical case or the violet case. Okay, so the difference in the velocities in one from 1 to 2, and the difference in the velocities from u, u2, and vr and vr2 is the total head. From where I get this one? We return back to the original equation, which is, we didn't discuss a lot about it, but we said this, we need to keep it in the, any head in any fluid machinery, you can apply this for bell, you can apply it for Francis, you can apply it for pump, you can apply it. But because it was very easy to get manipulation with velocity diagrams before, yet we can still use it. What is stating that is the head is 1 over 2g, whatever, it is 2g because this is, or remove it, it will be energy per mass flow rate, is the kinetic energy you gained, or the difference in the kinetic energy, which is mean in the actual velocities, plus the change in the radial velocity, plus the change in the relative velocities. Okay, this one we understand it. From Bernoulli even it is half 1 over 2g v1 by, it is okay regarding the h. Okay, but why this one? Why we adding this one? See, u is a change in the velocity due to the radius of the impeller itself. For an example, if you have an impeller like this, okay, and it is rotated in this direction, because you change in the radius, so the velocity going to change, which is the u itself. While you forcing the fluid to go in bigger radius, rotational radius, you are giving it more and more energy. So change in the velocity from the inner radius to outer radius, it is resulting increasing an energy inside the fluid. Okay, and what is one? This one is same like here, dot in yellow. You see here the area, you see here the area, or it can be an opposite case. This less this, and this is a rotation, and this is area is big and this area is small. So changing in the area will create change in the relative velocity by more or less. In changing in the relative velocity by more or less, going to do what? Going to increase or decrease the kinetic energy, which is converted to the head. Okay, so it is the diverging space passage. Okay, or by the way, or it can be due to friction. There is no diverging or converging, but due to friction in the passage of any passage, let's say the passage of the impeller or diffuser, due to the friction itself, so the velocity here is less than the velocity this one and 2. So also this static energy loss, or in some case energy more, or some case energy less in kinetic, it is resulting in the head. So it is whatever is, this is bigger or this is bigger or whatever, this is term in minus or plus, whatever, but it is become like this. So this is a general equation, which is we are going to took full from the rotor itself, from the dynamic motion, and this one is a static, uh, what you get. Okay, for example, if you have a violet case, where it is, like here, you have a violet case. Okay, the violet case is higher radius to a lower radius. So from higher radius to a lower radius, you are reducing U. So go here, from higher radius to lower radius, reducing U. So this one is less than this one. So we are getting more head, which is the benefit of the Francis turbine. Okay. So let's put the same equation again here. So this is a general case. Okay. And this is a static part and this is a dynamic part. Let's break it down here. And by the way, this is from the velocity component. So as it is similar like before, it is VW2 U2 like centrifuge compressor divided by G, and we can state that the degree of reaction, what we stated, like what is happening in the static divided by what happened in dynamic. So this is a static divided by the dynamic. Okay, just for a point of view. Later we're going to continue with the gas and steam turbine with all its significance, and we're going to know some other if difference between the impulse and the reaction. Then we'll open another subject later.